Hello, everyone. Thank you for joining us. I'm very happy to introduce today Professor Matthew Walker from the Toyota Technical Institute in Chicago. His research focused on machine learning-based solutions that allow robots to learn, to understand, and interact with people, places, and objects. Matthew has investigated these areas in the context of different robot platforms, including autonomous underwater vehicles, self-driving cars, voice commandable wheelchairs, mobile manipulators, and many other interesting platforms. Matthew has obtained his PhD from MIT, where his thesis focused on improving the efficiency of inference of simulations, localizations, and mapping. So any questions that you can have during the presentation, you can leave them on the chat. We will be keeping an eye or ask them at the very end. And I'm very happy now to leave Matthew all the stage. Thank you so much.
Thanks, Patricia, for the introduction, and thanks for having me. I'm very happy to be here, albeit virtually. Hopefully, we're back to doing things in person. So as Patricia said, that I'm happy to take questions during the talk. So please raise it in the chat, and hopefully I or someone else will see it. Or if you're able to, just speak up if you can unmute yourself. So I'm going to talk to you about one line of work my group has been working on for the past several years. And this is this idea of jointly learning an agent's physical design and its computational reasoning capabilities. But before that, one thing I like to do is just give a brief intro to TTI Chicago, Toyota Technological Institute Chicago. It's a mouthful for people who are not familiar with it. So TTI Chicago is a philanthropically endowed graduate level computer science institute. So endowed by Toyota, hence the name. We're not part of Toyota. You can think of us like a computer science, graduate level computer science department and university in one. So we're like a little mini university in many respects. We have 11 tenure track faculty and then 10 research assistant professors. These are fixed 3-year endowed positions, so hard money, not soft money. And we are graduate only, so masters, but primarily PhDs in computer science. And even in computer science, we're fairly focused. So it's computer science theory, machine learning theory, and what we call machine learning applications. So that's computer vision, that's robotics, that's speech, NLP, and computational biology. And that's really what we focus on. We have roughly 42 PhD students. We have a very close affiliation with UChicago. Many of us have appointments there. So we advise students at UChicago. We're the TTI and Kitty, for those of you who are familiar with Kitty. And with that, one of, I guess, 2 shameless plugs that I'll have during the talk. And so one is that TTIC is hiring. So that's tenure track, research track, and postdocs. TTIC is an excellent place, so very research focused. So tenure track faculty teach 1 quarter a year. So it's about 10 weeks of teaching. You can teach more if you'd like, but there's no obligation, but you get paid for 9 months, like most universities. But so very research focused. Research assistant professor is this 3-year endowed position. So it's hard money. You get a competitive salary. You can raise more money. You can raise a summer salary if you want. So you can be a PI on grants. Some do, some don't. No teaching obligations or opportunities, but you don't have to teach. And it's a great stepping stone for people who say want to go into a tenure track faculty position, but maybe they want a little bit of time to build up their CV. So you can do that without starting your tenure clock. Or someone who wants to go into industry, but wants to get more academic experience. So definitely please keep that in mind. And if you look at our alumni page, we have people at leading universities and companies. Okay, so with that, so I lead the Robot Intelligence through Perception Lab. And so as the name suggests, we work on various perception problems for robotics. And this can span things like natural language understanding. So we've done a lot of work in instruction following, natural language generation for robotics. More recently, we've been working on self-supervised 3D vision, transfer learning. I'll talk a little bit about that at the end of the talk. Tree Hoon, who recently graduated, co-advised with Michael Mayer, was working on a new neural memory architecture. And we have some students that are working on more theoretical side of reinforcement learning. Okay, so we focus on perception. So say, for example, you're trying to design a system to do semantic segmentation. So hopefully everyone can see this video. So it's a video, I don't recall what data set this is, but segmenting the image into meaningful regions and labeling them according to their categories. I'm sure many of you are familiar with semantic segmentation. So people, trees, cars, road, et cetera, et cetera. So many people are focused on this aspect, assuming that they get the image as input. How do I process the image as quickly or as accurately as possible? So the computational reasoning side of things. But what if you also had the luxury of changing the sensor design? So you imagine you have some parameterized design space that models the sensor. So this is where you're putting sensors, maybe in the CMOS array, and what color filter is on top. So light coming in from the environment hits these sensors, and depending upon their allocation, you get this image. In this case, it's a collection of RGB values. And then that gets fed to some architecture, typically today a neural network architecture, some inference network that performs the task, in this case, semantic segmentation. So segmenting the person, in this case, from the background. So there's two problems here. One is the design, if you have the luxury of designing the sensor. And again, the other is the computational reasoning. And so just very quickly, another example of that might be designing a robot manipulator for some pick and place or more general manipulation tasks. So in this case, you have, and what most people focus on is the design is fixed. I'm going to take in image streams, maybe tactile data, whether it's gel site or what have you, on the fingers, and I'm going to figure out what the right controller is that allows me to manipulate the scene. But we can pretty easily fabricate robots. So imagine now you could actually modulate the design of the robot as well to aid the computational reasoning. That's another example. And I'll just step through this last one just to motivate it, because it's a little bit more tied with what I'm going to discuss next. I don't know if some of you might be familiar with the Bayer pattern for imaging sensors. So with a camera, you have a sensor array where you have these photo sensors, and there's a filter on top of each one, a red, a green, or a blue filter that is just a pass-through filter for those colors, eliminates everything else. And so one sensor is going to be sensing red, the next one next to it might be sensing green, and there's a particular pattern on which these filters are arranged on the sensor. That's called a Bayer pattern. And then what you do is you de-Bayer the image to aggregate a red sensor with the neighboring green, and then blue to get RGB values. And so imagine you're doing that. You get your image, that's the sensor output. And then you're going to feed that to some neural network. Maybe you want to reconstruct demosaicing, you want to reconstruct the scene, et cetera. And so imagine now you're actually able to modulate the design, move the filters around. Is it possible to come up with a pattern that's better than a Bayer pattern for this downstream task, or this set of downstream tasks? And so this is an actual result from one of our former RAPs doing this, comparing the results with this learned sensor allocation versus just a Bayer pattern. Okay, so I'm going to be talking the first bit about design and computational reasoning in the context of sensors, but a different application that, arguably may be more easily understandable in the context of robotics, and that's beacon-based localization. So as Patricia said, back in my PhD, I did a fair bit of work in the underwater domain, and have just recently started getting back into that. And so underwater, as with any robotics application, having the notion of being able to estimate the pose of the agent is important, right? Localization. Unfortunately, whereas GPS works outdoors, GPS does not work underwater. It's attenuated by a couple centimeters of water. So what typically people will do is they'll put these acoustic transponders in the environment, these beacons, and they'll ping the AUV, the vehicle, and then based upon time of flight readings, you can triangulate where the vehicle is. And so there's somewhat of an art in determining where these transponders are placed in the environment. Indoors, if you've been to an airport, you may have seen functionality that allows you to localize yourself in the environment using your cell phone. So that's using Wi-Fi access points in the environment to figure out where you are in the environment. Right? So you have these coupled problems now. Where do I place these beacons? Let's say it's Wi-Fi access points or the transponders for LBL, long baseline navigation. You may have to decide which channel should these beacons broadcast over. And then now that the agent is getting these noisy readings from these beacons, or sensors are getting these noisy readings if it's going the other way around, how do I infer whatever phenomena I'm interested in this case, localization? How do I figure out where the agent is from these noisy sensors? And again, most people treat these problems as being independent. So there are various rules of thumb that people have traditionally gone by to determine placement. So one classic is referred to as the art gallery problem. So the idea is, and that's on the right-hand side, is the idea you have some art gallery and you want to place security guards around the art gallery with the constraint that every region of the environment, every piece of art is visible by at least one security guard. So that's the art gallery problem. And that's a commonly used approach to figuring out where to place these beacons. With inference now, a very standard approach, particularly with Wi-Fi beacons, is that's what I'm showing on the lower right, is to basically walk around the environment, build a map, and for each location in the environment, you look to see which access points you can talk to or you see, and you look at their signal strength. So that's what these bars are showing here. And you use that as a sort of a fingerprint for that location. So if you're in this location, if you're in this location here, that's what the fingerprint looks like. And hopefully it's distinct from the others. So then at test time, your inference is just a nearest neighbor lookup. You walk around with your cell phone, you look to see which access points you can see, their signal strength. You go back to this database and you do this nearest neighbor lookup, and you, whatever the best match, you associate that with your current position. So that's one example. Another example that's very closely related, just to touch on, this is very recent work just by this past year by a student in Daniela Rus and Wojciech Matusik's group. They have a robot manipulator. So that's what we're showing down here, this toy gripper here. And they're deciding where to place sensors on this gripper in order to, say, classify the object that it's holding, or even to regress to its geometry. And so you have this decision where initially you might start out saying that the sensor distribution is uniform on this gripper, but some locations are better than others, depending on maybe the type of objects that the robot might infer or the inference algorithm. So can you then, in a data-driven fashion, figure out where to place the sensors? And again, please, if there are any questions, interrupt me. Okay, so that's what I'm going to talk about in this first part. Design and reasoning in the case of sensor deployment and inference. And so what do we need for this data-driven method? So we need, one, some representation of the environment. We need, importantly in this case, and you'll hopefully see what the advantages are, it's a differential model of signal propagation. A set of a design space, so namely where we can possibly place sensors and on what channels they can broadcast. That's the input. So we're going to feed this to our algorithm. And then what we get as output is an optimal sensor placement. So place the sensors here in the environment, or you can imagine here on the gripper. Their optimal channel allocation. So one is broadcasting over channel 1, another one on channel 16, and then the spatial inference function. Okay. So just a cartoon diagram as to how we formulate this. So we have our environment here. This satellite dish corresponds to the agent we want to localize. This is you with your cell phone walking around a mall or an airport. And then you have these candidate beacon locations where the color indicates the channel that they're on, right? So that's the beacon location. And again, the color indicates the channel. Okay. And so nominally what we're going to have in it is for each candidate location, we have a binary indicator. So this is going to be X here denotes that there's no beacon there. Blue is channel 1, red is channel 2, et cetera, et cetera. So ideally, that's what we would like, this binary indicator value for each possible candidate location in the environment. And that's going to tell us whether or not there is a beacon there or a sensor there, and in this case, what channel it broadcasts. And so for a candidate location, we're going to assume we have some signal propagation model that says for a particular allocation of beacons, that's the IL, and for a particular agent location, here's the signal that you should observe. Here's what we expect you to be able to see, right? So that's this function psi. And then we're going to feed that to some inference network. It's going to be a neural network. I'll make that a little clearer later. And we want to output the estimated location. So the task simply is to find the sensor allocation, so where to place them and on what channels, and the inference function after the parameters of the inference function, such that we minimize, in this case, like the L2 error between the predicted location and the ground truth location. And so here's a block diagram of what this might look like. And so this takes as input a candidate robot or user location, and a beacon allocation, a sensor allocation, again, where to place the sensors and on which channel. that gets fed through this forward model. This is the signal propagation model. So then that means that at that location V, here's a vector representation of all the signal strength or whatever, what have you that you're going to see. That gets fed to the neural layer, or in this case, the set of neural layers, so the inference engine, and that outputs an estimated location. Okay, so what we'd like to be able to do is optimize this, very much like we optimize neural networks. And in fact, it ends up being the same way we optimize neural networks, is we compute some loss, and then we can back propagate that loss to the beacon, to IL, beacon location and channels. Unfortunately, this is not non-differentiable, right? We had this hard assignment of beacons. There's a beacon there or not, and if there is, it's broadcasting on channel 5, okay, or whatever channel it was. And so we do a soft approximation to that. So we have the soft max, where we have WL as a set of real numbers of size C plus 1. So C is the number of channels, again, 1 meaning that there's no sensor there. And now we can take the gradients through. So again, nominally, this would be a hard assignment, but in actuality, we have the soft assignment. And again, the key is that we're assuming that psi and F are differentiable. F is our neural network. We'll use a neural network for inference, so that's differentiable. And we're going to formulate psi as being differentiable. And in effect, what we essentially can do, if what we're able to do, if we do this right, is model the beacon allocation as a layer in a neural network. And so this just becomes a bigger neural network with one layer modeling where the beacons are and what channel they're broadcasting on. So now we can optimize this in much the same way, or really the same way that we optimize neural network architectures, just using off-the-shelf stochastic gradient descent to optimize this. Okay, and so we have some temperature parameters, and we may have some schedule on alpha through training, et cetera. And I'll talk a little bit more about that later. So that's the basic approach. So what we do is we again minimize this L2 loss on the predicted location. That's on the right-hand side, where again, we're taking this F is our inference, psi is our signal propagation model, both of which we're assuming are differentiable. So parameterized by theta. So we're going to minimize the expected loss here. And then we may have some regularization penalty on top of this that you can imagine, say, discourages having too many beacons. And so again, if these are differentiable, we can optimize this via stochastic gradient descent. Okay, so we test this on on several floor plans, and I'll just go through the results very quickly, then move on. But these are the three of the floor plans that we've evaluated on. I should say this was published at IROS a couple of years ago. This paper, I should have the pointer, and the code is all publicly available, and I'll show the link to that later. So we have our RF propagation model. Again, this is taking for a particular location in the environment V and a particular beacon allocation, which again, in practice is going to be soft. What signal do you see at each location? That's what this is modeling. And so we have a reasonably sophisticated signal propagation model that is accounting for attenuation due to walls. It's accounting for channel interference, et cetera, for noise. So we have 2 noise parameters here. So it's again a reasonable signal propagation model, and that's what we use. Our neural network, our inference network is a neural network architecture that takes as input the signal strength S, and then we feed that through a series of fully connected layers with ReLU and then max pooling layers. But again, a very simple neural network architecture. And as I mentioned, it might be beneficial to regularize, and actually I'll show that it is even in the context of training, but have some penalty on having too many beacons. Again, if you can imagine that this is Wi-Fi access points, they're not free. So you may want to, there is a cost constraint to placing them around the environment. So you might want to incentivize the framework to learn an allocation that is sparser for if nothing else, cost reasons. Okay. And so that's what we're going to do. And I'll show actually, and we'll see in a bit, that actually having a regularization penalty actually improves the performance. Okay, so what we do is we take our environments and we sample a large number of locations in the environment, and for each location we sample, I think it's 5 or 10 instances of noise, and we run our algorithm on this. And what we're looking at is the RMSE error. So the root mean squared error over all samples at all locations. Again, so this is samples over the noise parameters again, and then sampling over each location. And that's what we're visualizing here. So blue is low RMSE, yellow is high error, and so you can. And this is showing a thresholded assignment. Because again, our algorithm is outputting a soft assignment. So at each location, there's some likelihood of there being all the channels, though in most locations it's very, very small. And so we threshold that, or this might be just max, I don't recall. And this is showing the sensor placement that it learned. Okay. And so we look at a few things. So one is RMSE, as I mentioned. Another one is you can look at worst case RMSE. So again, for each location, we have a set of samples over the various noise parameters. So at each location, we look at what is the worst error. And then another thing we look at is failure rate. So what is the percentage of locations in the environment for which the error in their estimate is above some distance? So how many locations, again, this is all normalized. So how many locations, so if you imagine the width here as being 100 meters, how many locations are estimated with an error greater than 10 meters? How many greater than 20 meters? And how many greater than 50 meters? So various ways of trying to get a sense of how well this method works. Does it do well on average, but have a lot of outliers, or what have you? And so we did this with a number of handcrafted baselines. So we handcrafted beacon locations in the environment using one of the heuristic methods for choosing where to place beacons. And the first thing we wanted to do is, okay, well, does a neural network mechanism inference architecture make sense? Or is feed forward better? The neural network is nice because we can back propagate it when we're optimizing. But again, maybe a neural network, or sorry, K nearest neighbor, which is really has been up till recently the state of the art, is better. And we found that it's not. Nearest neighbor, the neural network based inference outperforms the K nearest neighbor based method for all of our maps that we evaluated on, and both handcrafted beacon placements. Okay, so that gives us some sense that confidence in the fact that neural network is a better strategy for inference. And we've seen this in practice. There have been several papers of late that also similarly use neural networks for localization and more generally inferring some spatial phenomena for sensor reading. Okay. And so what I'm showing here is this table. It might be a little bit difficult to parse here, but again, the first 4 rows are basically what I showed previously in the bar chart. So there's a handcrafted maps, handcrafted allocations with either K nearest neighbor or a neural network based inference. And the last 3 rows are different regularization strategies for our method. So one is we have a low regularization penalty. So again, nothing really incentivizing it to have as few beacons as possible. And we find that the network the algorithm learns an allocation, this is what's on the left-hand side, that has 183 beacons, so quite a few, and you can see the error is better than all of the baselines, but not as good as what the methods I'll speak to in a bit. And then we found that, well, what if we just add a high fixed regularizer? So we really penalize having a lot of beacons, having a lot of sensors in the environment. And we found that, so in this case, it went from 183 sensors to 12, so an order of magnitude less. That did increase the error, slightly. So both RMSE and worst case RMSE, in fact, all the errors went up. And then we found that actually, what if we anneal this regularization penalty? And we find that if we anneal it, we get an allocation that has twice as many beacons, but still far lower than either the baselines or our learn method with a low regularizer. But at the same time, significantly outperforms all the baselines, all the variations of our algorithm, as well as the baselines, with one exception. So we could see in the failure rate, one of the handcrafted baselines actually works better. So again, some evidence also that maybe our handcrafted ones are reasonable. So this is just showing that the beacons evolve. But again, in practice, this is a soft assignment. So we're viewing the hard assignment. So very quickly, again, I think this is with the annealed regularizer. If I remember, it looks about 25. It very quickly converges on this allocation strategy. So we looked at other things. Was there a question?
Yes. Can I ask? Hey, Dieter. So if you do multiple runs with random initialization, does it always converge to a similar configuration then in the end, or are there kind of local minima that look very different?
I'm trying to think. I don't recall. I think that there is some variability. I think some of our environments were symmetric. Certainly in the case of symmetries, it's not going to be the same. I think if I remember correctly, what would happen if you look at, if I could stop it, let's see if I can stop it. So okay, so with this method here, if you can see my pointer, so in the lower right, I don't know, I don't remember what channel blue is. Let's say it's channel 8. Yeah, I don't think it really matters if channel 8 is down there versus channel 16. So if we did another random seed, I believe it, could equally as well put channel 16 there. But again, I think certainly there is some convergence to a local optima. So it could be that next time it discovers something that's quite a bit different. I would expect with the annealed regularizer, it would still discover the same number of beacons, but the location might differ.
Okay. But the overall, let's say, quality of the localization you get out of these different, you would expect to be very similar.
Yes, yeah. And so that's what when we ran this, we sampled the various noise and we ran it from scratch a couple of times. So we did look at that. Yeah, thanks for good question. Yeah, so one thing we did is we looked at some things like how sensitive is our how sensitive this method is to say different parameters that we can choose. So again, this is the high regularizer, if I remember, or maybe this is a different map. So initially we have with what the original version of the algorithm, the vanilla version of the algorithm, it has, I think this is 12 beacons. So I'm looking at the top here. And we said, well, how does our method evolve? How does it differ if the properties of the transmission change? So for example, what if there's very little attenuation due to the walls? So, as you can imagine, if there's less signal attenuation, I could probably get by with having fewer sensors, fewer beacons, and that's indeed what we found. If there is high noise in the transmissions, we need more sensor readings to mitigate this noise. And so we find that it approximately doubled the number of beacons. If we allowed ourselves, and again, you can see similar, not surprising effects on RMSE. So when there's higher noise, it has a greater number of sensors, but that still increases the estimation error. We looked at changing the number of channels from 4 to 16, and we find that fewer channels increases the RMSE, perhaps not surprisingly because there's more interference, but really didn't affect too much the number of beacons that get allocated. Okay, so that's just one example. And we've been looking at this idea of coupling design with inference in a number of areas. And another one I want to just touch on is, there is sound for this, but I think sound is not terribly important, is legged locomotion. And so I'm not a legged locomotion person, but I see this as a very interesting problem to look at for this coupled design and inference, because, well, as an undergrad, I worked a little bit with Mark Spong at University of Illinois on passive walking. And so there was a lot of, some seminal work by Tad McGeer, who was an aeroscientist I think from Canada in the 1990s, on discovering if you have a good understanding of the dynamics of legged locomotion, and you are very careful about, you could build a design to exploit those dynamics, and that's this limit, it's hard to see, but this limit cycle in the upper left, you can realize these legged robots that exhibit passive or ballistic walking or near ballistic walking, meaning that they locomote due to gravity, very little energy required for locomotion. And this is Tad McGeer's walker. And then in the middle, I'm showing a video from Andy Ruina's lab at Cornell, and he has a number of these that are able to walk. And really their success comes down, in a big part of it, is having a solid understanding of the dynamics and a design that exploits the dynamics, really in some sense, putting intelligence into the design, into the dynamics. And we see that, something similar to this, or at least exploiting the dynamics, has made things like, Atlas. And I'm sure all of you have seen, the amazing videos that Boston Dynamics puts out. And this is, again, I don't know what their secret sauce is, but, my understanding is a lot of it comes down to having a very solid model of the dynamics that can be exploited. Osimo in the lower left, there is, again, an understanding of the dynamics where if you have the feet large enough and you do a zero moment point control, you can get stable gaits. Okay, so again, this idea that that the design, if done right, allows us to do things with the control that we may not otherwise be able to do, such as ballistic walking or highly agile maneuvers. And so these are coupled problems, and this is not this has been known for some time. Certainly there have been evolutionary methods in the 90s, probably predating the 90s, on evolving creatures and their motion primitives. There's been more work recently using learning and optimization. So work by, I don't know if this is the one, or Russ Tedrick at MIT, and Daniela Roos has done some work on trajectory optimization, where basically, you would imagine, you can imagine how you use trajectory optimization to learn the gates. But now if you can actually add the parameters of the design to the model, you can actually do trajectory optimization, not only over the gates, but the parameter of the design. And so these methods have shown to work to achieve, good results, both in terms of the capability of the designs, but they typically require, again, with trajectory optimization methods, full knowledge of the robot's dynamics, including a model of collision. They require a good initial design of the robot and the policy or the trajectory, the initial trajectory. Okay. And so we had a paper, our paper came out in 2019. It was an ICRA paper, and there's since been about at the same time in follow-on work on doing this in a model-free fashion. So again, that's what we're going to do, a data-driven fashion, where we only require that the robot's structure be defined a priori. So this is the morphology, how many legs there are and how many links there are in each leg. But we're going to, in a model-free way, learn to make the legs longer, shorter, larger diameter, smaller diameter, and the control policy without any constraints other than a max and min range on how big and the long and what the diameter can be. But that's it. And so the way that we formulate this is as a reinforcement learning problem. So unfortunately, it's not clear to us how we can do this in a way that would allow us to back propagate all the way through, like we could in the context of sensor allocation. So we formulate this as an RL problem. Specifically, we have some MDP where we have a set of states, and I'm sure many of you are familiar with MDP, so I don't want to belabor the point. But critically, we have a set of dynamics that we don't know, and our goal is to solve for the design R star, and the parameters of the policy. This is going to be a neural network policy that maximize expected long-term reward, discounted long-term reward. Okay, so we want to do this, and there's a paper, I think a movie by Rod Brooks, Faster, Cheaper, Out of Control, and we're sort of playing off of that. So faster, better, cheaper. It's a model-free, data and task-driven approach, design and control. And we can't do this exhaustively. We can't exhaustively optimize over the space of robots and policies. It's not tractable. So one approach you can imagine that might be reasonable is to take whatever our design space is, and if it's continuous, we're going to discretize it, or we may just sample from it, and we get a bunch of samples. So this is a 2D design space. Maybe it's length of a leg and the diameter of a leg, say in the cartoon setting. And so for each sample, what we're going to do is we're going to train a separate controller. So that's this controller or policy pi theta that takes as input a history of observations. It might, in this case, I'm showing 2, it might be 4, and then outputs an action, joint torques or joint velocities. Okay, and so for each design, in this case, there are 5 of them, we train a separate controller for that robot. And then we look at their overall performance and we pick the one that's the best. Okay, well, now here's a, of these, at least, an optimal design control pair, the design policy pair. And we go with that. We'll show that is sensitive to finding suboptimal designs. And so what we're going to do instead is hope to find one controller that we can use across all the designs. So one controller to rule them all. So we're going to have a controller that takes as input, again, the history of observations, but also takes an input the parameterization of the design. So now this controller actually learns to adapt to the different designs. And I'll show empirically how we found that actually helps us. And I'll speak to that a bit. So again, what we're going to do is we're going to perform gradient-based optimization over the expected reward, over the design distribution and the policy. We're going to model our design distribution as a mixture of Gaussians. And so we're going to be optimizing over the parameters of that mixture. So the mixture weights, the means, and the variances. And then again, as I said, train a single controller for this task. And so that's our, and so this is just a pictorial view of what we have. So again, sort of in the spirit of RL, we have our environment here, and everything on the left of that is our agent. And we're going to break it up. We have our control policy that's taking in observations from the environment. It's spitting out actions. That's going to give us our next state. The environment's going to return our next state and our rewards. We're going to back propagate through that to update our design distribution and our control policy, and then wash, rinse, repeat. Again, of course, it's not as simple as that, but and I'll go through it in a bit. So in particular, we're going to alternate between training the design and training the policy. So you can imagine what we do is we start off with, again, we have constraints on the size. The rope, the leg can't be less than epsilon in length and can't be more than, 5 meters, whatever our upper bound is. But we start off with effectively a uniform distribution over that. So very high variance and equal mixture weights. And we're going to sample from that. And you can imagine initially when we start training our controller on robots sampled from this distribution, they're not going to work terribly well, right? Because they haven't had enough time to learn, particularly when we want a controller that's able to generalize across designs. And so what we do is we allow the algorithm to train the controller for up to a certain number of iterations. Again, that's a hyperparameter. And then we go back and update our design distribution. And I'll show that again pictorially. Okay. So we have our mixture of Gaussian's distribution. Again, in this case, I'm just showing one mode. I don't remember how many modes we ended up having. I think it might be in a few slides in a bit. Okay, so what we're going to do is we're going to take our distribution and we're going to sample from it. We're going to sample some number n of different robot designs. For each robot, we're going to take our current policy and we're going to execute in the environment. And that for each robot is going to give us this trajectory of state, action, reward tuples up to some horizon or the end of an episode. So computing these under the policy. Then for these trajectories, we're going to compute our policy gradient and use that to update the parameters of our policy. Again, this is a fairly shallow neural network that we're using, and we're using PPO for this. And then what we're going to do is, or again, repeat, sample a set of robots, and then compute the total reward for these robots. And then we're going to use that to update the parameters phi of our parameter space via, again, policy gradient methods. Okay. So fairly, at a high level, it's a fairly straightforward algorithm. Again, there's some, subtleties in terms of when and how you alternate between training the controller and updating the controller and updating the policy. And so we evaluated this on OpenAI's Gym on a set of walking domains. So I'm sure many of you are familiar with this, and the code is available on Chip's website here. Hopper, walker, and ant, and we just use the default rewards. So, but before I get there, we parameterize the robot in terms of the length of each link and its diameter, mass, etc. Our policy is a fairly shallow three-layer neural network, 10 activations. Our robot distribution is a Gaussian mixture with 8 components, randomly initialized. And we consider different terrain. So walking on flat terrain, walking on inclined terrain. We played with the friction to get a sense of how robust our design pairs. Again, sort of analogous to what Dieter was asking with the beacon place localization. But again, now how robust are they to variations, test time variations? And we compare with the handcrafted designs from RoboSchool and also baseline. So one, analogous to what I said before, where we sample a set of designs. For each design, we train a controller and we pick the one that's best. But you can also think of the design as being a hyperparameter in the optimization. So we use Bayesian optimization as another baseline. And so what I'm showing next is an evolution of our design, so our proposed methods. So each column here is different iterations in training, starting with early on in training. So what I'm showing here is I'm showing the design and various points in the trajectory to get a sense of, again, for the same amount of time. So again, I don't remember what, maybe this is 5 seconds. And so initially our design gets about this far, or a design controller pair. And then with the hopper, as the design evolves, you could see that what it's learning is to make the upper body, upper torso very long, but also very light, very narrow. And it's able to get about 2 or 3 times as far as the proposed design. Walker, we see something similar. So again, it learns to make the upper body very thin and lightweight, and then learns these bounding gaits. And then with the ant robot, again, it learns to make the legs longer and lighter, thinner, so lighter. And so now it gets these, again, much more efficient gaits. And then we compare this to what we might get out of, again, the default design, which we already know, This is the optimal gait. And then for the same period in time, so if you compare, like say for the walker, we get this far in, let's say 5 seconds. Bayesian optimization doesn't do too poorly. So it learns again, having a thin body, and it gets, maybe 3/4 of the way. And then, similarly with other robots, other designs. Okay. And then again, we do this on level, and it actually, this is level terrain. This is inclined terrain, actually, just to look at a sense of how those affect behavior. And again, I'll go, this is probably, a bit, this is like basically what we're visualizing here is we run our algorithm a number of times with different random seeds. These are the blue dots. So farther to the right is better. And so for our, I don't remember how many samples we drew, but this is showing the reward for our method. Bayesian optimization, the red triangles, green X's are the random sampling, that random sample baseline. And the dashed lines are showing the performance of the default design with the optimal controller. And we see that, we're readily or easily outperforming for, in almost all cases, all the baselines. There are some instances where actually the Bayesian optimization does well, but we still are outperforming. So one thing that we can do that's fun with this is, again, we have a distribution over designs. So imagine at some point in training, what we do is we take our controller, we take our design distribution, and we draw, let's say, 1,000 samples from our design distribution. So that's going to give us 1,000 different robots. For each robot, we execute the corresponding policy on that robot and look at the reward. And we can plot that. So what we're looking at here is, like, vertically, it's a heat map of reward for, again, I don't remember, it was maybe 1,000 different designs at each time step. So we can see early on, the designs are random and the controller is not very good. So most of our designs, if you can see, sorry, I'm pointing in the wrong window, get 0 or very little reward. But as we update the controller and update the design distribution, so at the bottom, I'm showing the design distribution being updated. So it looks at roughly about 0.2, or actually probably 0.1, we start updating the design distribution. And very quickly, the variance drops and it converges to this particular design. And we could see that in the evolution here, that almost all the samples are tightly coupled in the design. Again, not surprisingly. And so similarly in reward, they're converging. And so we see this for the various robots. Okay, so just let a video play. I'm a little bit long on time. Check my time. Okay, so they're just showing various points during training. And I think this video is on our webpage. So this is showing our final design with this very, non-obvious gate. Again, there's a saying that, simulation is doomed to succeed. So I think there's certainly some of that, and I'll talk a little bit about that next. But for the sake of time, I'll get going here. I'm sure you've seen many videos like this. So, but of course, I'm a roboticist. I like seeing these things work in practice, and all of that work, and you can probably understand why, was done in simulation, because of the sample complexity. But I want to actually realize these robots. And so that over the past year or so, there's been this collaboration with one of our research assistant professors, Audrey Siddall, who graduated about 1.5 years ago from the University of Michigan, on looking at joint design and control in the context of soft robotics. And so Audrey's certainly the soft robotics expert. So I can't, but I can speak to some extent of the advantages of soft robotics. One that she is very passionate about is this inherent safety that comes with the soft bodies. And so we were looking at this in the context of, again, soft robots. Say I want to do some task that's moving around a man-made environment. I want to learn what is the right design. And, the design space in many ways is far more complex, or the space candidate set of designs is far more complex. And what's the corresponding control policy? In this case, we're going to be doing this with bodies for which we can control the pressure. So what's the right policy that controls the pressure in this area? And so looking down, we're evolving our designs based upon interaction with the environment, this reward signal. This toy example, we might knock something over. And we end up learning a design and control policy jointly that provides us with more agility in the environment and more safety, but then we want to be able to realize this. And I'll skip through a lot of this, just talking about the challenges of the design space. We do this in the context of pneumatic localization, so I'll let this play. So each one of these legs, or what we refer to as actuators, has in these teeth a void. And so we can actuate we can apply a pressure, and that pressure gets applied to all the voids. So in this case, we have 4 different control inputs nominally. Well, in this case, it's actually 2 in this case, but we can control each of the legs. Now, these legs are tied to one of 3 pressure regulators. So now you can imagine our design space, and I'll show that in a bit, just showing that, we actually are doing this in practice, not just in simulation. So again, we have these they're called new nets. So this is our design space. So in some sense, maybe like the beacons, we have a disk, and we can choose at one of 8 different locations. It's actually more now, whether or not to place a leg there, an actuator. And if we do place the actuator, what pressure regulator it's connected to. And I'm drawing 3 here, but 2 regulators rather, but we actually have 3. So we can we can choose not to place a leg or an actuator, or we can choose to place it and then couple it with another leg. And so what we want to be able to do is, again, very much like we were doing before, jointly learn the design and control policy, but do it in a way that such that the resulting design is not only physically realizable, but can actually be transferred to the real world. And this is, a hard problem. Modeling the dynamics is far more complex. And I know some people here are, I'm sure, more of an expert in this than I am. But it's very complex for these soft bodies. And so what we're using now, and we're actually looking at using, hopefully NVIDIA has a soft body simulator that can be simulator for soft bodies that can be actuated. Right now we're using SOFA, which is an open source simulator, and it numerically solves the differential equations using finite element methods. They're part of hopefully too much the fidelity. We've spent a lot of work on model order reduction to improve the efficiency of this model. And so we're able to speed it up 8 times.
Matt?
So now we're getting somewhere, maybe this is realistic, but now there are problems, right? Because we have this reduced model, and we get these designs that are not physically realizable. They float and they blow up. That's maybe not too much of a problem in the sense that doesn't get the agent, it gets rewarded when it makes forward progress. So it's not going to get any reward for doing this. So it has no incentive to do that. But the biggest one we saw is this sliding. So it learns if it inflates. And we found this actually. We started training our policy, and we looked at our plot. We were getting really high reward. And we looked at it like, that's great. But then we looked at what happens, and it's just, magically moving forward. Okay, so we don't want that. So again, we spent a lot of time trying to calibrate our design to best match reality. And again, that's what these plots are. But again, don't worry too much about the plots. And we've gotten our, a reduced model that actually does not, is not violating physics in these ways. And so what I'm going to show is some very early results. I think this is about now, maybe a week or so, a little over a week old, training this in simulation. And so again, we're learning both the design and the control policy. And what I'm showing here is the reward of the mode of this distribution. Okay, we have a distribution over designs. And then what I'm visualizing is the mode of this distribution with the corresponding control policy. And so this is early on in training. It learns that it can put 2 forelegs in the front on different pressure actuators, regulators. And it's getting some reward. So it's based on where the center of the disk moves. And it's moving a little bit forward. So it's getting some reward. And it learns it can drop a leg and maybe get a little bit more reward, and it does that. But all of a sudden, again, we have other samples that are not the mode, but that are doing much better. And all of a sudden, it recognizes that it can do far better. And it learns this design with 3 legs, 2 hind legs and 1 leg in the front. And it learns this gait that allows it to make forward progress. It's not flying by any means, right? It's not terribly agile, but it is moving. And we took this policy, and we did have to apply a scaling parameter to the pressures, but that's it. And we ran it on our real robot in the lab, and we get this gait. And there are some subtle differences in the gait with friction, but there was no domain randomization, no data augmentation, no adaptation. Again, we did have to scale our pressure parameters by, I think it's, at one point, I don't remember what the number was, but that's it. And we're able to get this, like the next day, we just ran this on our robot and we're able to locomote. Again, it's not moving terribly fast, but it is moving and comparable to what we saw in the simulator. So I know I'm low on time, so I just wanted to, wrap up with some very recent work. And I'm sorry, I'm going to switch to a different slide deck. Again, in the context of sim to real transfer, right? There's been a lot of work, and rightfully so, paid to sim to real transfer, or more generally, this this distribution shift that you see, right? And this is not just in, in RL, this is true more generally in machine learning, but I'll be talking about this in the context of RL, where you train on a set of environments. This might be a legged robot, or it might be a soft body robot. But then at test time, and this is what your policy sees, this distribution in green, but you go to test time and the distribution looks very different. In this case, this cartoon case, there's no overlap. This is from the distractor control suite from a recent paper by Stone and others, where if you're not familiar, they put distractors in the background, or they change the camera angle, they change the color of the agent to have a simulated version of this domain shift. But again, we see this in practice, right? If it's a robotics application, the lighting at test time is going to be different than at training time. And it's even more exacerbated if it's trained simulation test in the real world. And so if you look at this and you take a state-of-the-art method like Dr. Q v2, and you look at how well it performs as you increase the intensity of the distractors, and I don't have time to go into what that is, but making the disparity more intense, you see, perhaps not surprisingly, that as this distribution shift increases, you get far more inferior results. And so one approach to doing this, and this is taken from seminal work by Tobin and others with Peter Abeel, is you might do domain randomization. So what we're looking at is we want to train a robot in the bottom to do a manipulation task in simulation, and we hope that it transfers to the real world. Our simulator is not perfect, both in terms of the physics as well as the rendering. So we wanted to be able to do essentially is do domain randomization, take this training distribution and spread it out as much as possible, so that now we have some support, some overlap with the test distribution. And that's what we're visualizing here, different samples. That comes at the expense of forcing our network to try to learn in situations that are very different from what we'd see at test time. But we don't know what we'll see at test time, so we just make it as wide as possible and hope that our model has enough capacity to capture this, right? And so this we refer to as invariance through memorization. So in practice, it tends to perform worse. Again, maybe our model doesn't have the right capacity, so it may be impossible. No matter what we do, there are probably going to be conditions that we encounter where there's going to be no overlap. And so just very quickly, I'll speed through this for the sake of time. Basically, our intuition, just real quickly for this, is that there is some underlying representation that is preserved, like nominally the pose of the agent. If we knew the pose of the agent, and in this case we know that's a good input, that is not affected by distractors. So if we're able to recognize that, we actually could do transfer in a readable way, or could have better overlap. And so basically that's what we do, is we learn a representation of the state space or the input space that is invariant to these distractors. And that's what this cartoon is looking at, is that there is a dimension, there is a representation for which there is far better overlap between training and test. And so the question is, can we learn that? And so just, again, very quickly, the way that we do this is we train in the undistracted environment. This might be in simulation, say, for example, and we train our policy that's in an inverse dynamics layer. And we're learning some embedding Z. And we train our policy, and then what we do in the training environment is we collect this buffer, sort of like a replay buffer, of all the embeddings seen in the training time domain. So this is a collection of Z's, embeddings, for which we know our policy works. That's the ones that we have our training distribution over. And what we want to do is we want to match our test time distribution over those Z's to our training time distribution. So we do at test time is we take our input, again, with distractors. This might be not in simulation, but the real world. We encode them, so we embed them into this Z, and we know if the distribution over Z at test time matches training, or as closely matches training, we have some. We're optimistic that the policy we train in simulation or in the trained policy is going to work well at test time. Now the question is, can we get those distributions to match? And so the way that we do that is we train a discriminator. And we try to trick the discriminator into not being able to tell the difference between a Z sampled from the training domain, so it's like a sample from the training distribution, and a sample from the test distribution, to force it to learn an embedding that, again, fools the discriminator. And we also have this inverse dynamics layer. So if you're familiar with PAD, something after deployment, I can't remember what it stands for now, but a very recent algorithm by Hansen, where they also use an inverse dynamics head. But we find that the discriminator significantly helps. Essentially, what we're doing is we're trying to force the distributions to match as closely as possible. And we do this without any access to reward at test time. Just we're executing a random policy at test time, collecting observations, and we're learning an embedding that matches that we've seen during training. Okay, so we'll go back to the results that we saw before, and we use our method, building off Dr. QV2. We find that we can significantly improve generalizability to this domain shift as we increase intensity of the variations, camera pose, video background, age and color, et cetera. Okay, so just wanted to touch on that. That's very recent work, a couple, maybe a week or so, actually no, a couple weeks old. So with that, again, I'll just go back and I'm over time. Again, I can be long-winded. Sorry, my last plug. If you're not familiar, IDO is something we developed, but was developed at MIT, and then we refined it in 2017 while I was at TTIC. And IDO is many things, but one thing we're using it for is what we call AI driving Olympics. So it's an embodied benchmark for machine learning and AI more generally. And so we're going to have IDO 6 at this upcoming NeurIPS. Unfortunately, virtual. NeurIPS is virtual, but we're encouraging people to participate. We have a simulator, and I know Dieter taught a Duckytown class. So I'm sure many of you are familiar with Duckytown. We're going to have auto labs, so you can run your Ducky bots on remote laboratories with ground truth localization that we get after the fact, et cetera. So yeah, it's a great platform in many respects, but it's a fun competition. And so with that, I just wanted to acknowledge several of the people that worked on this, current and former members at TTIC, a collaborator at MIT. And with that, just play this Monty Python skit, which I don't think I've ever seen in a walking talk, but I'm sure they've had it. I don't know why I've not seen more of it. But yeah, so with that, I'll take any questions.
Thank you so much, Matthew.
There's the Ministry of Silly Walks, if you haven't seen it. And I should say also the papers, with the exception of the last one, are all available on our lab's website. Both the beacon placement and the walking have project pages with videos, and the code is all available if you want to play with it.
Thank you. I invite the members of the audience for a very brief question, if anyone has.
So on the co-design between the parameters of your robot and the gates, where you're doing the sampling and things like that, that seems very related to what we've seen with where people use evolutionary algorithms for that kind of co-design. Do you see any advantages of your technique over these, or
yeah, so I think, and I've talked to people. So yes, I was talking to Andy Ruina about this, because he saw a lot of this work earlier on in legged locomotion, where they use genetic algorithms or various evolutionary methods. Those, in my experience, tend to be more susceptible to local optima than ours, by, again, maintaining this. Again, I think for us, having this distribution over the designs helps us exploit coupling between, coupling in the benefits of different designs that you don't get with these evolutionary methods. Bayesian optimization is a more sophisticated way, and we see that does perform reasonably well, but we still see that our method outperforms Bayesian optimization as well. But yeah, so for a long time, this, the strategy was these, survival of the fittest, genetic algorithms, evolutionary algorithms, and they are still used today. But again, we found that the performance that we get is actually better. And one interesting that I mentioned that said I would touch on, but I didn't, is one interesting that we found, sort of along the lines of an evolutionary method, is that, so, as I said, we have one controller that has to try to generalize to all the designs from our design distribution. And so we thought, well, presumably it would actually be better if we had a separate controller for each design. And so what we did is we took the final design that we learned, and we trained a controller just for that, fixed the design, trained a controller just for that. And we compared the performance of that controller design pair with the one that was learned with the controller that generalizes across design. And it actually, the one that generalizes across designs actually outperforms the one whose sole job it is to control this one design. So there's some advantage to the optimization of having a controller generalize across a design space.
Yeah, I guess robustness or things like that, right?
Yeah.
So you're not overfitted, yeah. Makes sense.
Well, but it's overfitted, but that's fine, because all I want to do is I take my optimal design, I train a controller on that. So it's fine if it overfits to that, but still the more general purpose controller was better.
Mhm. Thank you.
Thank you so much, Matthew. I invite everyone to thank the speaker as well. Unfortunately, we have to close the session because we are really on time, but thank you so much.
Thanks everyone.